Let's continue the ZEUS training, section 7, input cards for aerodynamic modeling. So these are the bulk data cards used for the aerodynamic model input of ZEUS. Of note here we have the body 7 and AEROZ 7 cards to define the surface mesh. We have the block 1 and block T cards to define the volume mesh. We have the PAFOIL 7 and PAFOIL 8 for airfoil definitions. We have the GAPZ and GAP1 cards to define or to help set up the volume mesh. They function similar to a AEROZ 7, except it does not define a surface mesh of the model. It just helps with the volume mesh generation. And then we'll go through the remaining cards as we come to them. Okay, this is the bulk data interrelationship for the aerodynamic geometry input. The kind of at the top level here, we have the AEROZ card, which defines the aerodynamic reference parameters. Then we have the block sequence, which assists in the overset mesh strategy, along with the block layer card. The mesh save card allows you to save or retrieve the flow field mesh. Then we have the block 1 and block T cards, which define the volume mesh for the automated mesh generation. These can refer to the Y zone Y cards to define the Y location of the Y zones. And then also it can refer to the mesh param card to control parameters for mesh generation. Then the block cards refer to the AEROZ 7, the GAP cards, and or the body 7 card. And these define the surface box generation. These cards can refer to an ACORD card, which defines a local coordinate system in which to define the surface panel. Then we have the PAFOIL 7 and PAFOIL 8 to define the airfoil sections for the AEROZ 7. And then for the body, we have the P-body card to define inlet panels. And then we have the SEGMESH card to define the body segment definition. This is the AEROZ bulk data card. The first field is the ACSID. This is not an ID field, unlike most other cards. This is an identification number of a Cord2R card, which defines a coordinate system in the structure model, where the x-axis is towards the pilot's face or towards the aft of the aircraft, and then the y-axis is the right-hand side. This allows you to define a local coordinate system for the structure model so that ZEUS can rotate the structure model to line up with the aerodynamic model. Remember that the aerodynamic model, the x-axis must be along the flow direction and the y-axis must be out the right-hand side of the aircraft. However, as you know with the structure model, the coordinate system can be completely arbitrary. X could be up. It doesn't really matter for the structure model. So with the ACSID field, the purpose here, it refers to a Cord2R card. This Cord2R card defines a local coordinate system in the Nastran basic coordinate system, where this local coordinate system is the aerodynamic coordinate system that you use to set up your model. So, for example, if the origin of your aerodynamic model is at the nose of the aircraft, then in the Nastran basic coordinate system, this Cord2R card, the origin of it must be at the nose, and then the x-axis points aft, the y-axis points out to the right-hand side, and the z-axis will point up. We always recommend using the plot arrow card, which we'll talk about later, which allows you to plot the structure grids along with the aerodynamic model. And this plot will apply this transformation to help make sure that you've correctly rotated and translated the structure model so that it lines up with the aerodynamic model. So using the AEROZ card, you can quickly validate that you've correctly done that transformation. Okay, next is the XZ-Sim field. We have 3 options. This is a character string. It can either be yes, no, or H2F. For X2F, or sorry, for yes, this says that the XZ-Sim is yes, so we have a symmetric model. So both the aerodynamic and the structure models are half-span models. So you'll usually see this with older models. So the structure model is half-span, and the aerodynamic model is half-span. Now for the aerodynamic model, it must be modeled on the right-hand side. For the structure model, it can be modeled either on the right-hand or the left-hand side. So if the structure model is modeled on the left-hand side, then we'll have to go to the next field, flip, and set flip equals to yes. So for flip equals yes, ZEUS will mirror the structure model from the left-hand side to the right-hand side. For the other options, flip should be no. So next we have XZ-Sim equals no. So this means that both the aerodynamic and the structure models are full span models. And then lastly we have H2F. In this case, the aerodynamic model is a full span model, but the structure model is a half span model. And then once again, the flip option would be available here. If your structure model is on the left-hand side, you'd want to use flip to flip the structure model over to the right-hand side. Now in this case, ZEUS internally will mirror all of the structure grids so that you have a full span structure model. And then the ID numbers of these mirrored grids is negated. So if you have, for example, grid ID of 101 is on the right wing, then when you do the spline of the aerodynamic model for the left wing, you would refer to grid negative 101 to refer to that grid. So in this case, you want to import both the symmetric and the anti-symmetric mode shapes from your finite element solution. Moving on to FMM unit. This stands for the mass unit of the structure model. Now this field is not used, and we'll explain that why in the next one here. So FML unit is the length unit of the structure model. Now the model units of the structure model and the aerodynamic model must be the same. So this FML unit is the length unit for the structure model, and it's also the length unit for the aerodynamic model. And it must be one of inches, feet, meters, millimeters, centimeters, kilometers, or none. Now the mass unit is automatically determined based on the length unit. And the force unit will always either be pound force or newtons. So if the length unit, for example, is feet, then the force unit would be pounds, which means the mass unit would be slug. So the restriction here in your structure model, whatever units you choose, the force, the derived force unit must be either pound force for the English system or newtons for the SI units, the metric units. So if you have inches as your length unit, then the mass must be slinch. If you have meters, then of course the mass unit would be kilogram. If you have millimeters, then the mass unit would be metric ton. And if you have kilometers for your length unit, I'm not sure why you would do that, but if you do have kilometers as your length unit, then your mass unit would be grams. So that is a restriction of ZEUS, that your force unit must be either pounds or newtons, and there's no way to get around that. If you try to put something into the mass unit, ZEUS will just ignore it. Now personally, I type in what the unit is in the mass unit, and that's purely for documentation purposes. So if my length unit is inch, IN, I'll type in slinch or SLIN for the mass unit, just to remind myself that's what the mass unit is. Okay, next we have ref C, which is the reference chord length, and the units here are in the FML unit, are model units. So the FML unit and FMM unit, I'll be referring to those as model units, as opposed to analysis units, which we'll come across later. So ZEUS has two unit systems, model units and analysis units. The bulk of the input will make use of the model units. Next, we have ref B, which is the reference span length. Remember that the reference span is from the left wingtip to the right wingtip, even for half span models. But of course, this is an arbitrary number, so it's whatever your aerodynamic guys tell you is your reference span, that's what you would use. Ref S is the reference area, and then ref X, ref Y, and ref Z is the location of the aerodynamic moment center for computing the aerodynamic force and moment coefficients due to the rigid body motion. So our notes here, we've talked about the mirrored grids, we've talked about the flip. This is what ZEUS uses to calculate the coefficients. So for example, the CL, the lift coefficients, is L over Q infinity times ref S. So this is where ref S, ref C, and ref B are used in ZEUS. Next we have the AEROZ bulk data card. This is an aerodynamic wing component. So for any lifting type surfaces or flat plate type of elements in your aircraft, you would use the AEROZ. So WID is the identification number. Label is an arbitrary character string that you can use, or you can leave it blank. ACORD field refers to an ACORD bulk data card to specify a local coordinate system. So if you do make use of this field, then all of the coordinates listed in the AEROZ will be in this local coordinate system. N span is the number of span-wise divisions of the wing component. Note here that the difference from the aerodynamic module of Nastran, MSc Nastran, N-span and N-chord in Nastran are the number of boxes, whereas in ZEUS and ZEUS, N-span and N-chord are the number of divisions. So for ZEUS, we have the restriction that N-span must be greater than or equal to 3, which would mean that the number of boxes in the span-wise direction must be at least 2. And then N-chord is the number of chord-wise divisions. And once again, N-chord must be greater than or equal to 3. N-chord can be negative, which means that the first box is half the size of the remaining boxes. Normally I don't make use of this option. If I want to do something like that, I would make use of the LRCHD and LTCHD fields, which we're going to see in a minute, to specify custom chord-wise divisions. Okay, L-span refers to an AE-FACT card to define the span-wise cuts of the AEROZ. Now, if L-span is blank, then by default, ZEUS will evenly distribute the span-wise cuts. So if your N-span is 3 and L-span is blank, then the divisions would be at 0%, 50%, and 100% of the span. If you don't want even cuts, then you make use of the L-span entry. So this refers to an AE-FACT card where you refer to the span-wise divisions in percentage of wingspan. So the values will go from 0 to 100. Z-Tech field is unused. That's left over from ZEUS. PAFOIL 7 refers to a PAFOIL 7 or PAFOIL 8 bulk data card to specify the airfoil sections. If PAFOIL 7 is 0, then the AEROZ is assumed to be a flat plate. So most often you will want to refer to a PAFOIL 7 card to define your airfoil. The next row here is for the root side of the AEROZ, and actually with ZEUS, you always want to remember that the root is actually the left-hand side of the AEROZ, and the tip side is the right-hand side of the AEROZ. So on the right wing, or the right-hand side of the aircraft, the root is the left-hand side, and the tip is the right-hand side. And in the old days, we would only ever create half-span models, so the root was always the left-hand side and the tip is the right-hand side. However, on the left-hand side of the aircraft, you still want XRL, YRL, ZRL to be the left-hand side of the wing, which is actually the tip of the wing. So the nomenclature is kind of confusing. But remember that the root side actually means the left-hand side of the wing, and the tip side is actually the right-hand side of the wing. So XRL, YRL, ZRL are the X, Y, and Z locations of the left side of the C-Aero7. And this is in the local ACORD coordinate system. And if ACORD is blank, then this would just be the global ZEUS coordinates. RCH is the length of the chord of the left-hand side of the wing. And then LRCHD optionally refers to an AE-FACT card to specify the left-hand side chord-wise divisions. So if it's blank, of course, even divisions are used unless you had a negative number up in the end chord. And then if you can refer to an AE-FACT card and to specify your own chord-wise divisions of the wing. And then ATTCHR is not used. Once again, that's left over from ZERO. But we do have the field here. So if you're copying a model from ZERO and then you have some number in here, ZEUS will just ignore it. It won't throw an error. It will just be ignored. And then we have the tip XTL, YTL, ZTL, which is all the right-hand side. So we have the XYZ location of the right-hand side of the wing. We have the length, and then we have the custom divisions. Now, unlike most other bulk data cards, the ID number, which for C-Aero7 was WID, does matter. Internally, ZEUS needs to give an ID number to each individual aerodynamic grid point and each aerodynamic box. And you cannot have any duplicated grid IDs or box IDs. So in this example, we've used 101 as the wing ID of this C-Aero7. And for this component, we have end chord equals 4. So we have 4 chord-wise divisions. So we have 3 boxes. End span is 5. So we have 5 span-wise divisions. So we have 4 boxes. The numbering starts at the leading edge left-hand side, or the root side of the C-Aero7. So the first box is the same as the wing ID of the C-Aero7, so it's 101. And then we move from the leading edge to the trailing edge at the root side of the wing, and then we move each column of boxes here to increase the ID number. So the boxes will increase up to end chord minus 1 times end span minus 1. So with our first ID being 101, we have 3 times 4, which is 12. So the last ID here is 112. The IDs, the grid IDs start at 101 and then finish at 120. So for this numbering scheme, this is why when I choose an ID number for my wing, I'll use, for example, 101 versus 100. I like to count starting at 1. So if my ID of this C-Aero7 is 101, then my boxes are counted 101, 102, 103. If I were to use 100 as my wing ID, then of course my box IDs would be 100, 101, 102. So most often my wing IDs, I'll choose 1001 or 10,001, something like that, and then I'll increase as my next C-Aero7. If my first one's 10,001, my next C-Aero7 would be 20,001. My next C-Aero7 I would use 30,001, and so on. Now, as I said, you can't have any duplicated IDs. So if you have a second C-Aero7 and you choose, let's say for example, 111 as your ID for the second C-Aero7, you'll notice then that we now have 2 aerodynamic boxes with ID 111, and then also grid IDs of 111, which is not allowed. So ZEUS will give you a fatal error and say we have duplicated IDs. So you want to make sure that you have sufficient spacing between ID numbers of all of your C-Aero7s, which is why I'll usually use increments of 1,000 or 10,000. That gives me plenty of room to have as many C-Aero7s, and then each of my C-Aero7s can be as big as I want. So of course the limiting factor here isn't the box IDs, it would be the grid IDs, because there are more grids than boxes. Okay, moving on. And I talked about this left-hand side. When the wing is on the left-hand side, you want the left-hand side of the wing to be the root side, and you want the right-hand side to be the tip side for purposes of the C07 definition. Next, we have the PAFOIL 7 to define the airfoil, and this card is referred to by the C07. So we have the ID field, which is referred to by the C07. ITAX is an identification number of an AE FAT card used to specify the X coordinate locations in percentage of chord where the thickness and camber are specified. And this will apply both for the root side and the tip side, which remember is the left-hand side and the right-hand side. So for example, if you want to define your airfoil using 101 points, then ITAX might be 0, 1, 2, 3, 4, and so on up to 100. So at these x-coordinate locations, you will define the thickness and camber at both the root side and the tip side. So that leads us next to ITHR, which refers to an AE FAT card which lists out the half thickness of the airfoil on the wing root side. And so the thickness is specified at each of these ITAX locations. Next, we have ICAM-R, which specifies the camber of the airfoil. And this is relative to the chord of the, or it's normalized by the chord of the airfoil. And then next we have RAD-R, which is the leading edge radius, once again normalized by the chord. And then we repeat, we have the thickness, camber, and radius for the tip side or the right-hand side of the C07. So we have an illustration here of an airfoil. So this is the wing mean plane here. So note that the leading edge of the airfoil can be below the wing mean plane. So the wing mean plane is where the flat plate C07 would be located. And then this is the two-dimensional airfoil. So we have a leading edge radius normalized by the chord. And then this line here is the camber line. And then our half thickness is illustrated here. Note that the, let's see, where is that? Remark 1. Yes, okay, remark 1. If the ITAX field is positive, then a cubic interpolation is used between the airfoil points. So that's illustrated in figure B here. So if we have these 4 points defining the airfoil and ITAX is positive, then the resulting airfoil uses a cubic interpolation. Now, if we actually want to create this diamond type of airfoil shape like this, then we would specify ITAX to be negative. So once again, these same 4 points will get this resulting airfoil shape when ITAX is negative. So that uses a linear interpolation between the points instead of a cubic interpolation. Positive camber here is based on the normal vector of the C07 macro element using the root edge and then the leading edge, which basically means as long as you follow the convention where the root side of the C07 is the left-hand side and then the tip side in the definition is the right-hand side, then positive camber would be up. So that is why we tell you always specify the root side is the left-hand side and the tip side is the right-hand side. Next we have the PAFOIL 8, which is an alternative definition for the airfoil. ZEUS internally will just convert the PAFOIL 8 into a PAFOIL 7 card. The PAFOIL 8 can be more convenient. I always use the PAFOIL 7 because it's a more direct control, but you can use the PAFOIL as well. So the PAFOIL 8 for the root And tip, you'll refer to a foil sec bulk data card to define the airfoil section. And then additionally, we have the rad-r and rad-t to define the leading edge radius on the root and tip side. Next, we have a print flag, which allows you to print out the resulting airfoil shape. Then we have interp field, which can be a character string, either linear or cubic. So this replaces the ITAX option from the PAFOIL 7. So normally you would set this to be cubic. And then reverse allows you to flip the airfoil upside down. So the upper and lower surfaces are simply reversed if reverse is set to yes. Okay, next we have the body 7 card to define a body macro element. So we have BID is the body identification number, and similarly to the CAEROZ, the box IDs and the grid point IDs are based off of this body ID. Next we have the label, which is an arbitrary character string. IP body 7 field refers to a P-body 7, which allows you to specify inlet aerodynamic boxes. ACORD field refers to an ACORD bulk data card. This specifies the body center, line location and orientation, and then also the body 7 is defined in this local coordinate system. Next we have NSEG. It's called NSEG because it's the definitions left over from ZEUS, but in ZEUS we have the restriction that the number of segments of the body 7 must be equal to 1. So this NSEG must be either 1 or positive 1 or negative 1. If NSEG is positive 1, then the grid lines projected on the YZ plane in the wing body region are automatically determined by the number of circumferential points specified in the SEGMESH bulk data card, and for NSEG equals -1, then the automatic grid line generation is deactivated, which means you must use the GAPZ bulk data card to define these projected YZ, the Y lines on the projected YZ plane. If you have a body with no CAEROZ adjacent to it, then basically you'll want to set NSEG equals 1 to allow ZEUS to automatically generate all of the grid lines for you. If you have a CAEROZ adjacent to a body 7 and they're in the same block, so if you have a fuselage and wing, then most likely you'll want to set NSEG equals -1 and use a GAPZ card to manually control the vertical spacing of the grid lines above and below the wing. And we'll see some examples of that later. But just remember, usually if you have a body alone in a block, NSEG will be +1. If you have a body along with the CAEROZ in a single block of mesh, then NSEG will probably be -1. Next, we have the ID mesh field, which refers to the identification number of a SEGMESH card. The SEGMESH defines the body segment. Next is fact dy. This controls the number of span-wise X lines on the XY plane for modeling the width of the rectangular box that embodies the body 7 macro element. And this is only used if the body 7 is referred to by the block or the block T bulk data card. And then fact dz controls the number of horizontal X lines on the XZ plane. Most often you'll want to use the default here. So all this means is, let's say for example, you have 10 segments, circumferential segments around defining the circumference of your body. Then fact dy means ZEUS will say, okay, I'll then use 10 span-wise X lines on the XY plane, and then I'll use, with a fact dz of 1, I'll use 10 horizontal X lines on the XZ plane to define my my ZEUS mesh, which is usually adequate. But you can change the number by changing this fact dy and fact dz to be greater or less than 1. Next we have z bottom or z bot. This is the z location of the bottom of the rectangular box that embodies the actual surface of the body, where if it's blank, then the default is the lowest Z location among all of the surface grid points on the body. And then likewise, Z top is the Z location of the top of the rectangular box that embodies the surface of the body. And we'll, on the next slide, we'll see what these mean. You'll want to use the A chord field because of this remark too here. The x-axis specified by the A chord bulk data card defines the center line of the body macro element. Whereas if A chord is 0, then the x-axis of the ZEUS basic coordinate system is used. Okay, so let's look at these examples of adjacent wing and body situations. So in this example, we have our body 7 defined here, and then we have some C-AERO7s out here which define the wing. Now, like I said, in this instance, you'll probably want to set nseg equals to -1 to deactivate the automatic grid line generation of the body, and then you'll want to define a GAPZ card, which is shown here, to control the spacing. So we have the spacing above and below the wing, so we have the grid points defined here, and then you can see the top of the GAPZ lines up with the top of the body 7, and then the bottom of the GAPZ lines up with the bottom of the body. And then outside of this region, ZEUS will automatically grow the grid lines below the body and above the body. Now, in figure B here, in this case, we have a body alone. So here we have nseg equals +1, so ZEUS will automatically fill in these grid lines in this vertical direction. Furthermore, the fact dy and fact dz are used. If we count the number of circumferential grid points here, we've got 1, 2, 3, 4, 5. Okay, so we've got 21 around the circumference here. So if we were to count these grids, we should get 21. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20, okay. So instead of 21, we've got 20. And then the same thing here, we'll have 20 grids in this direction. So that's where the fact dy and fact dz. If you decrease fact dy, then we would have fewer boxes in this region here. And then similarly, if we decrease fact dz, we'll get fewer boxes in this direction. But normally you'll just want to leave them as the default because then the fidelity that you model your body 7 with is kind of mirrored in the fidelity of the resulting grid. Figure C here is the same model as figure B. It's just the side view. Next, we'll look at the Z top and Z bottom. Now, normally, if Z top and Z bot are blank, then ZEUS will take the top and bottom of your body here and use those as the body box boundary. Now, if you have a vertical tail, as shown here in this F16 model, we do not want these C-AERO7 panels embedded inside the body box because inside the body box there is no flow solution. There's no flow because it's inside the body box. So instead, we want the top of the body box to be at the root of the tail. So in this case, we have to manually specify a Z top, which can be this line. And then now our entire vertical tail is outside of the body box. Not only that, the root of the vertical tail lines up perfectly with the boundary of the body box, and that's the ideal case. Now you'll say, part of my canopy here is penetrating outside of the body box. Is that a problem? No. Remember, with the transpiration boundary condition, the slopes of all of the aerodynamic panels making up the body are simply mapped to this rectangular body box of the mesh. And as we've seen, the transpiration boundary condition works quite well. So this is not a problem. Similarly, here we have a C07 on the underside, so we'd want to make sure that our Z bottom is set such that it intersects with this C07 as well. And then if we go back to this figure, the right side boundary of the body box actually lines up with the root of the wing right here. And you can see that some of the body actually it goes outside of that body box, but once again, that's okay. That doesn't matter because we're just going to project all of the slopes of the body onto this body box. So the resulting body box, and actually this in this figure, figure A, we don't have the tail modeled. So the top of the body box is actually the top of the canopy. If we were to include the tail in this picture, then that would be approximately about right here. So in that case, our gap Z would only go up this high, and then our body box would only go up this high. So the resulting body box would be here, and then would come down here, and then approximately down here due to that ventral fin. So our gap Z definition would match that of the body Z top and Z bottom definition. Okay, moving on to the SEGMESH. This is the body segment definition of the body 7. So ID mesh is the ID that's referred to by the body 7 card. N-axis is the number of axial stations or divisions of the segment, and N-rad is the number of circumferential points of the segment. The YR shrink and YL shrink allow you to or control the sheared grid lines in the resulting body if you want the grid lines to be sheared along the surface of the body. And I believe we have a picture of that. Yeah, we have a picture on the next slide, so we'll revisit these. Similarly, ZT shrink and ZB shrink are for the upper and lower surfaces. So we'll talk about those on the next slide. And then reduce is a factor to define the rate of the grid shearing. And once again, we'll talk about that on the next slide. Okay, next we have an open-ended input. So however many axial stations you have, so your n-axis, whatever that is how many rows you'll have. So if n-axis is 3, as shown in this example, we now have 3 rows. So each of these rows refers to one axial station of the body. So the first field is I-type. This is the type of the input used to define the circumferential box cuts. 1 is the simplest. It's simply a body of revolution. So if you have a simple missile or fuel tank or something like that, or a very simple body, then that can be a body of revolution. 2 is an elliptical body, and then 3 is an arbitrary body. With an arbitrary body, the user must specify each of the XY coordinates of each of the grid points of the panel. Next, Xi is the X location of the axial station, and of course the X must be in ascending order. As a special case, you can have 2 repeated rows with exactly the same X value. And that's because ZEUS does allow you to define 0 area surface panel boxes. So if you imagine the F-15, for example, the inlets, the engine inlets, the way to define those in ZEUS, if you want to model those accurately, you would have to have repeated X coordinates so that you can have that box that is perpendicular to the incoming flow. Because the inboard and outboard section of the intake on the F-15 is perpendicular to the incoming flow. So the way you'd have to model that is you have 2 SEGMESHs with that particular X location. But that's quite complicated geometry. In the vast majority of cases, the Xi will be ascending and you won't have any repeated X coordinates. Next is the camber allows you to define the body camber of this particular station. Usually this is only used with the body of revolution or elliptical body modeling types. So if you have a body of revolution but then with some camber, you can use the camber field. If you're using the arbitrary body, you probably don't want to make use of the camber because that just makes everything complicated and confusing. But basically the coordinates at this particular X station will then be shifted by this camber amount. Next we have the YR and ZR. So for the body of revolution, YR is just the radius of the body of revolution. For the elliptical body, YR is the semi-axis length of the elliptical body parallel to the y-axis, and ZR is the semi-axis length of the elliptical body parallel to the z-axis. And then for the arbitrary body, these are not used. So next we have the IDY and IDZ. So moving back to the body of revolution or elliptical body, for body of revolution and elliptical body, I type I can be used. If IDY is 0, then the NRAD number of cuts are evenly distributed around the circumference. If IDY is greater than 0, then IDY refers to an AE-FAT card, which specifies the NRAD number of circumferential cuts in angles in degrees, which must start at 0 and end with 360 for the full span model, or if you have a store hanging under the wing on a half span model, of course that would still be a full circle, so it'd be 0 to 360. Or with a half span model, when your body is on the symmetry plane, then it would range from 0 to 180. I've actually never made use of this option, but you can if you want to. Now moving back to arbitrary body, IDY simply refers to an AE-FAT card, which lists the y coordinates of the NRAD number of points at that X station. And then IDZ refers to the AE-FAT card that specifies the Z coordinate locations when you have an arbitrary type of body. And then lastly, we have the shrink field. This is a character string which can be none, all, or any combination of YR, YL, ZT, and ZB. And then, so if we activate the shrink option, which we'll soon talk about, then this one will allow you to activate the shrink for that particular X station. Okay, so let's talk about the shrink option. In this case, in this figure, we have a very simple slender body. Now by default, remember that we create a body box, so it's just a rectangular type of box, and so the body box, it just looks like this. It's a rectangular box, and when we look here at the front view, this would be our body box, and then ZEUS will map the slopes of the surface mesh onto the body box here, and then use the transpiration boundary condition to model the effects of this body in the flow. However, with a very simple model like this, where we don't have any attached wings, we can make use of the shrink option so that the mesh is sheared to follow the surface of the actual body. So if we want to do that, then the YL shrink and YR shrink, which remember were up here in the first row, these are the Y coordinate locations where the shearing stops taking place. So in this case, YR shrink is set to this value, which means from here and then to the right, the grid is not sheared. But within here, within this region, then the grid is allowed to be sheared. And then you ask, okay, so at which X stations is my grid sheared? On each X station row, we have the shrink card. So in this model, if shrink is set to all, on all of my X stations, you can see that the grid is sheared at every X station. So that our grid now follows the the body. And so this is the top-down view, so we can see the left and the right-hand side. And then this is from the side view, so we see the bottom and the top. So similarly, we have ZB shrink and ZT shrink. Outside of these values, the grid is not sheared. Within these values, the grid is sheared. So we can see that the grid is sheared on the right-hand side, the left-hand side, the top side, and the bottom side at every X station. So the shrink field was set to all for every axial station in this definition. Now, looking just at these two figures alone, you may think, oh, my Cartesian grid is just perfectly follows my body. But actually, no. At each individual X station, our body box is still a square. So on the left-hand side, the left boundary will line up with the left-hand side of the body, and then the top side will line up with the top side of the body, but the grid does not follow the curvature of the body. It's still a square. So our body box is a square at every axial station. However, the size of that square is changing at every axial station, so it's kind of following the shape of the body. So that is how the shrink option works. And then lastly, if we go back to this reduce field, that controls the rate of the grid shearing. So the default is 0.5, so we get kind of a smooth shearing. If you make reduce closer to 0, so if you use 0.1 for example, then the grid shearing, and actually I forgot which way it is, but basically the grid shearing will shift more towards the body side or the boundary side. So basically the 0.5 works the best usually, but if you don't like the resulting grid, basically you can play with that reduce field and change it to values anywhere between 0 and 1 and see what it does to the resulting mesh, and you'll soon get a feel for what it does. And actually this equation here is incorrect. We changed how the reduce works, and so this equation, this is the old equation, which yeah, ZEUS doesn't use this anymore. Okay, this is some pictures showing our body of revolution, our elliptical body and arbitrary body. So using the body of revolution, each axial cross station is just a circle, and then you can use the camber option to vary the camber as shown here. For the elliptical body, you can get something that looks like this. So our YRI and ZRI are used like this. And then the arbitrary body, you can create something that looks like this. Now for a half-span model on the symmetry plane, if nrad equals 9, the grids would be distributed like this. For a full-span model or for a half-span model with a store that's not on the symmetry plane, nrad equals 9 would give you this resulting model, because now the 9 points have to be distributed among 360 degrees rather than just 180 degrees. And then here's a figure illustrating n-axis. It's the number of axial cuts, and then n-rad is the number of cuts around the radial direction. Next we have the GAP card, which is a fictitious surface on the XY plane to assist the model generation. So from the viewpoint of your surface panel model, the gap is just a fictitious surface and it doesn't exist. From the viewpoint of the volume mesh generation, the gap just looks like another C-AEROZ. So ZEUS uses this gap card to assist in the model generation. So we have EID is an element identification number. The label is not used because it's a fictitious surface. And then we have ACORD, which allows us to define this gap in a local coordinate system. N-span is the number of span-wise divisions. Now, because of the way the gap is used, most often you'll want n-span equal to 2 because you're not using the span, or you're not using the gap card to introduce additional end span or span-wise divisions. You're using the gap card to introduce additional chord-wise divisions. So end chord is the number of chord-wise divisions. The default is 2, but like I said, normally you'll want to set end chord to a higher number because the whole purpose of the gap card is to introduce additional chord-wise cuts and to control the spacing of those chord-wise cuts. L-span refers to an AE-FAT card to control the span-wise divisions. Usually if end span is 2, then you would leave L-span blank because the two divisions would just be 0% and 100%. However, if you are using the gap card to control the span-wise divisions, we have an additional option where L-span can be negative. So remember, when L-span is positive, the AE-FAT values range from 0 to 100%, which is the span-wise divisions. If L-span is negative, then the values in the AE-FAT card are the actual Y locations defined in the global coordinates. So if you want to specify exactly where those divisions are in terms of the Y coordinates, you can use the negative option of L-span. Next we have XRL, YRL, ZRL, which is the XYZ locations of the root chord leading edge, or the left-hand side leading edge. Although with the gap, the left and right convention doesn't matter. And then RCH is the length of the root chord. And then LRCHD, usually you'll be making use of this field. When it's positive, then it refers to an AE-FAT card, which specifies the chord-wise division in terms of percent of root chord. And then if it's negative, then the values in the AE-FAT card are the X locations defined in the global coordinates. So of course the first X coordinate should be XRL, and then the last X coordinate should be XRL plus RCH. And then the next row here is for the tip side of the gap. So if we look at some pictures here where we might want to use the gap. So in the top figure, figure A, we have a wing and a tail in the same block here. Now if you do not have a gap card, then the resulting mesh might look like this, which is a bad mesh because we have very fine cuts along the wing, and then just after the wing we have this huge box size, then we have a second huge box, and then the tail. So ZEUS has a harder time automatically generating the mesh between two elements like this. It's not sure exactly what it should do. And so in this case, the user should specify a gap card to assist with the mesh generation. So in this case, we have two options here. Option B, we add a gap card just between the wing and the tail to specify what those divisions be, and you can see if we think of the gap just as another C07, we plop it down here, and then this is where the gap card is, and you can see that we've specified our chord-wise divisions as shown here, and then the mesh is generated like so. So we have a much better mesh. However, right here we do still have a kink kind of in the mesh, and so in figure C here, we've further refined the mesh by adding a second gap card right here, and that controls the mesh like so. So now you can see we've got an even better mesh generation using these two gap cards. The second instance where you'd want to use a gap is when you have a body and a wing, and then we have a launcher out here. So with no gap card right here, with a launcher here and the body 7 in here, we'll have grid lines being generated from the body coming out, and then we have grid lines from the launcher coming this way. And those two grid lines most likely will not line up with one another. So what will happen is we'll have uneven spacing of the grid lines, and ZEUS may even delete some of the grid lines if they end up being really close to one another. Now if we use a gap card, then we can ensure that the grid lines from the body and the grid lines from the launcher perfectly line up with one another, because we can make sure that the first grid line ahead of the wing coming from the body will then connect to the first grid line coming out from the launcher ahead of the wing. So if we look at the resulting figure here, you can see that we have a nice even distribution of grid lines because we've ensured that the grid lines from the body line up with the grid lines from the launcher. Furthermore, it's not shown in this figure, but we do have a gap card in between the wing and the tail to get as nice of a grid as we can here. And I think I've covered everything in the remarks here. Just further note here, all of the coordinates in the XRL, YRL, ZRL are in the local coordinates defined by the ACORD card. Next we have the GAP1, which is an alternative entry method for the gap. So this one may be easier to use in this specific scenario. If we have a wing and then a tail, and we want a gap card between them, as we just saw on the previous slide, we can actually use a GAP1 card. And now what this will do is ZEUS knows where the leading edge of this gap is because it lines up with the trailing edge of the C07 in front of it, and it knows where the trailing edge of the gap is because it lines up with the leading edge of the C07 behind it. So we have an identification number, and then C0L is the identification number of the C07 in front of the gap. So the trailing edge of C0L becomes the leading edge of the gap. And then C0T is the C07 behind the gap. So the leading edge of C0T is the trailing edge of the gap. End chord is the number of chordwise divisions. Almost always this would be set to 2 because I was thinking span. The chord number of chordwise divisions is for adding additional chordwise divisions between these two C07s. Y zone L is the Y location of the inboard edge of this gap. So in this case, this would be Y zone L, which doesn't have to line up with the inboard edge of the C07, but in this case it does. Let's skip AE fact L. Y zone R is the outboard edge. So in this case, you can see it happens to line up with the outboard edge of C0T, but it does not line up with the outboard edge of C0L. That's fine. So now let's go back to AE fact L. This is refers to an AE fact card to specify the inboard chord divisions of the gap card. So if AE fact L is 0, then we distribute the cuts evenly. If AE fact L is greater than 0, then the chordwise divisions are in terms of percentage of root chord of this gap card. And then when AE fact L is less than 0, then the chordwise divisions are the X locations listed in the AE fact card. And then AE fact R is the same, but for the right-hand side. N span is the number of spanwise divisions, and as I was trying to say earlier, almost always this will be set equal to 2 because your spanwise divisions set by your wing and tail here are probably what you want in the mesh. You don't want the gap introducing any additional spanwise divisions. So N span would be 2 and L span would be blank. However, you can use the gap to introduce additional spanwise divisions if you would like, or you can set the spanwise divisions to line up with that of the C07. So you can use N span and L span to do that. Next we have the GAPZ card, which is a fictitious surface on the YZ plane. So this is basically the same as the GAP1, except now we're controlling the Y lines on the projected YZ plane, or the vertical spacing of the grid. So we have the ID number, label is not used. We have ACORD, which specifies a local coordinate system for this GAPZ. N span is not used because now you cannot use the GAPZ to introduce additional spanwise cuts. So essentially N span is just equal to 2. N chord, oh, sorry, our, this should be NZ grid. So up here we have NZ grid, so this right here should be NZ grid. So this is the number of grid lines from the lower to the upper surface of the gap Z on the projected YZ plane. And then XRL, YRL. ZRL is the location of the root of the lower surface of the gap Z. RZ gap is the Z distance between the lower and upper surface of the gap Z along the Z direction. LRZ gap refers to an AE fact card to control the grid line spacing. So if LRZ gap is 0, then we use an even distribution. If it's greater than 0, the AE fact card is in terms of percentage of RZ gap from 0 to 100. And then if LRZ gap is less than 0, the AE fact card lists out the true Z locations. And these Z locations are defined in the local coordinate system defined by the A chord entry of the gap Z. And then XTL, YTL, ZTL is the same except on the tip edge. So let's go look at a picture here. So we have a fuselage and a wing here. So the top, so this on the left here is what happens if we set nseg equal to -1 in the body 7. So this body 7 will not introduce any additional Y lines on the YZ plane except one at the top of the body and at the bottom of the body. And then we have our horizontal tail here and our wing up here. And you can see that the wing and the tail automatically will add some grid lines above and below the wing and the tail, as shown here. But then because they're adjacent to a body, ZEUS does not grow these lines above the wing and below the tail. But then above and below the body, ZEUS will add these lines. So what we want to do here is control the spacing. So we add a gap Z. Actually highlighted here we have 2 gap Z cards, which is unnecessary. You only need 1 gap Z card. So we'll just look at the inboard portion here. We add a gap Z where the bottom of the gap Z lines up with the bottom of the fuselage body box. The top of the gap Z lines up with the top of the body. And then, so you have some options. You can either leave this region blank in the gap Z because we already have these grid lines from the wing and the tail, or you can see what these values are and use them directly in your gap Z. So in this example, we've copied the Z locations here to the Z locations of the gap Z. So the gap Z will perfectly line up with the wing. And then between the wing and the tail, you can see we've added these grid lines. And then above the wing, we've added these grid lines. Below the tail, we've added these grid lines. So now we get a much better looking mesh using the gap Z. So as I said, usually when you have a C-Aero 7 and a body 7 in the same block, you'll need to use a gap Z to have good grid spacing above and below the wing. Next we have the block card, which generates the rectangular block of mesh. So this defines the outer boundary of the rectangular block of mesh and selects the body's horizontal surfaces and vertical surfaces which are fitted into that single block of mesh. ID block is the identification number of the block. However, the ID block field can either be positive or negative. Now among all the block T and block 1, all ID numbers must be unique. And when ID block is negative, then residual smoothing for this block of mesh is deactivated. IACORD refers to an A chord card to define a local coordinate system for the block. And then X lead and X trail define the leading and trailing edges of the rectangular block of mesh, and of course X trail must be greater than X lead. Y left and Y right are the left and right boundaries of the rectangular mesh, and of course y right must be greater than y left. For a half span model, if this is your main block, then y left would be 0 because it's on the symmetry plane. And then z bottom and z top are the bottom and top boundaries of the rectangular mesh, and of course z top must be greater than z bottom. Next we have an open-ended input to define all of our y zones. So each row of this open-ended input corresponds to one single y zone. So our YL and YR are the left and right hand side boundaries of this y zone. And we have two different ways of defining the boundaries of each y zone. You can use a real number to type in what the y coordinate is of the left and right boundaries, or these can be integers which refer to a y zone y bulk data card, and the y zone y determines what that boundary is. Now note that the YL of a entry must be equal to the YR of the previous entry. So this y zone would be adjacent to this y zone, which means the right hand side boundary of the first y zone equals the left hand side boundary of the second y zone. Then for each y zone we have these ID fields. So these refer to the C07, Body 7, GAP, GAP1, or GAPZ cards. And note that we have 6 entries available. So if you have 6 or fewer elements in a particular y zone, you can just list out the ID numbers of those elements, and this will be the case the vast majority of time. However, if you have more than 6 elements that you need to put into one y zone, then the ID 1, the very first one, will be an integer or a dollar sign followed by an integer. For example, $1000. In this case, this 1000 refers to a set 1 card with that ID 1000. And then the set 1 card can list out as many ID numbers as you would like. Remember, the set 1 is unbounded. You can have as many integers in that as you want. So then that set 1 will list the ID numbers of the C07, Body 7, GAP, GAP1, and or GAPZ cards. So here's a picture of the of what the block looks like. So here we have a aerodynamic model in here, and then we have our block of mesh surrounding it. So if we look at this corner of the box, the coordinates here are x lead, y right, and z top. If we go to the opposite corner, this is x trail, y left, and z bottom. I don't think... we'll talk about this later in the mesh param card. But the rectangular block of mesh actually does not have to end up being a rectangle. So if our x growth parameter in the mesh param card is a negative number, then you can see that the boundary of the block of mesh conforms to the model. So this is our model, and so you can see we've got the leading edge is swept here. Now in the default case, these grid lines would all be sheared so that we end up with a rectangular box. But if the x growth is negative, then the boundary of the box is sheared to follow the shape of the aerodynamic model. And then that's also can be seen on the trailing edge here, where we have this shape, and the shape is replicated here in the boundary of the box. And we'll go over that again when we get to the mesh param card. And then here's an illustration once again of our y zones. So in this example, we have 11 y zones. So the block card would have 11 rows with all of the y zones. So in the first y zone, we just have this single C07. For the second y zone, we just have this one C07. And then for the third y zone, we have these two C07s. So note that the left and right boundary of your body, if you recall, going back to the Body 7 card, there was a Z top and Z bottom field in the body 7 card to define the upper and lower surfaces or points of the body box. However, there was no Y left and Y right. The reason is that the Y left and Y right boundary of the body 7 is defined by the Y zone. So this body 7 here is in zone 6. So the left and right boundaries of Y zone 6 will become the left and right boundaries of this body box. So if this body box penetrates outside of the Y zone, that's fine. That's okay, because we're just going to map the slopes of the body onto the resulting body box. Next we have the block 1, which generates a body-fitted mesh. So ID block 1 is the identification number. However, it can be negative, in which case the residual smoothing is deactivated. Next, ID body refers to the body 7 around which the body-fitted mesh is generated. IA chord refers to the A chord bulk data card, which is the local coordinate system where this block of mesh is generated. Next, we have X lead and X trail, which are the upstream and downstream boundaries of the body conforming mesh. R is the distance between the body surface and the outer boundary of the O type of mesh in the radial direction. So it's kind of the radius of the block 1 card. NR is the number of grid points along the radial direction, and then NR can be negative, and in this case the program will generate NR divided by 3 additional grid points along the radial direction inside the body. And the flow solution at those points inside the body is set to 0. This is recommended if this block 1 is embedded inside of a larger block, because we need a flow solution at all of those points to be able to interpolate back to the host block. But if the block 1 is your main block, then NR can be positive. You don't need a flow solution inside of the body in that case. Next we have the AEFACT field. If it is 0 or blank, then the grid points distributed along the radial line are determined by the program. So this would just be like a even distribution. If it's greater than 0, then it refers to an AEFACT card, which lists out the NR number of grid points distribution along each radial line in terms of percentage of the total length of the line. So this goes from 0 to 100. And then AEFACT can be a character string COS or cosine. In this case, we use the cosine distribution of grid points along each radial line. Next is X growth, which is the growth rate of the mesh along the x-axis. And then we have N source, W, tolerance, IT max, and ratio, which are parameters to control the 2D mesh generation around each section of the body. X wake is the length of the wake region behind the truncated end body divided by the body diameter at the end of the body. And then VISRAT, viscous ratio, is a factor to increase the Viz2 and Viz4 parameters. This allows the user to increase the numerical artificial damping only for this particular body-fitted mesh. And this option existed before we had the option in the MK param to list an individual Viz2 and Viz4 value for each block. So nowadays, this would just be set to 1, and then you could use the option in the MK param to list out the individual Viz2 and Viz4 parameters for each block. Or you could use this as well, whatever you find easier. Here's a picture of what the block 1 looks like. So here we have a much too complicated aerodynamic geometry to be used for the block 1, but this is just for illustration purposes. So you can see how the grid is grows out from the body like this. And so this is our R direction here. And then we have the X lead and X trail. And then the X growth factor controls how fast the X growth occurs in the mesh. For the 2D O-type mesh parameter generation here, for this remark, we have n source must be an integer 0 or 1. For n source equals 1, the Poisson equation is solved to generate the O-type of mesh. For n source equals 0, the Laplace equation is used. And W is a relaxation number to solve the Poisson equation, which must be between 1 and 2. The tolerance is a convergence limit for the Poisson iteration. And IT max is the number of iteration numbers for the Poisson iteration. And then finally, ratio is a threshold value to prevent the failure of the 2D mesh generation. And then for our wake here, behind the truncated in-body, the separated flow may occur, which is normally unsteady in nature. The unsteady separated flow may give a convergence problem to the Euler solver. So to circumvent this, it's assumed that the surface mesh, the body-fitted mesh, is extended by a length of d times x wake, where d is the diameter at the end of the body, which represents the streamline outside of the separated flow region. And therefore, the region inside the streamline is not part of the computational domain. Okay, next we have the block T, which generates a block of mesh to model a T-tail component. So you can see it looks somewhat similar to the block 1, except we have two regions here. We have our HT and our VT. So in the HT section, we have a block 1 type of input to define our Y zones. And then we have the VT section, so we have another block 1 type of input, but this specifies our Z zones instead of the Y zones. So let's take a look at why this is needed. Okay, let's look at remark 1 here. So modeling a T-tail configuration accurately using the block bulk data card requires the overset mesh. So we have one block card which models the horizontal tail, and then the other block models the vertical tail. So then you're going to rely on the overset scheme. However, the overset mesh sometimes may decrease the accuracy of the solution. Also, if both of the horizontal and vertical tails are included in one block card, then the ZEUS will change the vertical tail to be unswept, which is not correct. So to circumvent this problem, we have the block T card, which allows you to put both the horizontal tail and vertical tail together into the same block. So the block T will shear both the Z lines and the Y lines to get a good resulting mesh. So if we look at our fields here, the first row is the same as the block 1, and then we have the two sections, like I said. So HT, this is a character string that is HT, which triggers ZEUS to recognize the following as part of the horizontal tail section. So then we have Y center, Z center. These are the Y and Z locations in the local coordinate system defined by the ACORD card, where the horizontal tail intersects with the vertical tail. So in this picture, this point here would be our Y center, Z center. And then the tolerance is a fraction of the reference chord to delete one of the chordwise Y lines in the flow field if two chordwise Y lines are located within that tolerance. Next, IDELET refers to the delete line card to delete unwanted grid lines. Usually you'll not want to use that option. Next, we have keep LE and keep TE. This is the number of grid lines ahead of the leading edge to keep even if the mesh size is smaller than the tolerance times the ref C. And then keep TE is the same but for the trailing edge. And then we have the YL and YR. These are the Y locations of the left and right hand side of the Y zones. And this can either be the physical Y locations or it can refer to the Y zone Y cards. And then next we have the ID fields, which refer to the C07, body 7, gap, gap1, or gap Z. So in this picture here, in our HT section, we would have two Y zones, 1, 2. This would be the left left-hand side boundary of the first Y zone. This would be the right-hand side boundary of the second Y zone. And then this C07 would be listed in that Y zone. For the second Y zone, this is our left-hand side boundary, and then this is the right-hand side boundary of the second Y zone. This C07 would be in the second Y zone. Okay, now we move to the vertical portion. So we have VT, which is the character string VT to indicate that we're now on the vertical tail section of the block T. Next we have ZV low and ZV top. So ZV low is the lowest Z location, and then ZV top is the highest Z location of this particular Z zone. So in this example, ZV low would be down here, and then ZV top would be up here. And then we've got the ZB and ZT. These are for this particular Z zones. Sorry, ZV low and ZV top is for the entire block T card to be operating. So our vertical tail must be located within the ZV low and ZV top. So outside these locations, the Z lines will no longer be sheared. And then so we have the ZB and ZT to define the bottom and top portions of the Z zones, and then the IDZJ list out the components in that particular Z zone. So within each Z zone, we can refer to C07 cards, and then we can also refer to the GAP or GAP1 cards, but we cannot refer to the body 7 card. If you have a body 7, that must be in the horizontal portion. Okay, so let's look at another picture here. So we've already seen this option. Another option is here where we have a body 7. So once again, the Y center, Z center is where the vertical tail and horizontal tail would intersect each other. And then it's also, you can see the center of this body 7. So this body 7 would be listed in the horizontal portion in our Y zones, but it would not be listed in the Z zones. Now, the grid line size along both the Z-axis and Y-axis is critical to the solution accuracy of the solver. So we have our DZ. The DZ here in a normal block 1 is only determined by the wing, the horizontal surface. So the DZ would be some factor times the reference chord. However, in the block T, the DZ is determined by the size of the panel of our vertical tail. And then the DY is determined by the size of the box of the horizontal tail. So in this case, you want to make sure that this DY and this DZ are small enough such that the boxes sitting outside of the vertical tail and the boxes sitting on each side of the horizontal tail are small enough. So when you make use of the block T, your span-wise cuts of the horizontal tail and your span-wise cuts of the vertical tail near this intersection should be smaller than they normally would be, because the span-wise cut size is actually defining the size of the boxes for the adjacent surface, normal to the direction of the surface. So this DZ value is defining the height of the boxes that are sitting below this C07. So you want to make sure that those are small enough, and then that they grow at an appropriate size as you move away from this intersection. Next we have the block sequence, which lists out the ID numbers of the blocks for the overset strategy. So in this example, our block number 1 is our main block that contains the body and the wing. Block 2 contains the pylon and store, and then blocks 3 through 6 contain the fins of the store. So the block 1 is the main block. That's the largest block. That should be listed first in the block sequence, because the blocks listed first are the large blocks. The blocks listed last are the smaller blocks. So in this case, this block sequence card, G1 would be 1, G2 would be 2, G3 would be 3, and so on, because our ID numbers of our blocks follow this convention of the smaller numbers are the larger blocks. If you have all block cards, as we do in this example, the block sequence card actually may not be necessary, because ZEUS by default will just use the ID numbers of the blocks for the block sequence. But if you have the block 1, ZEUS doesn't just use the ID numbers, it will list, let's see, if the block cards will be first and then the block 1 would be last. So basically you always want to use the block sequence card just to avoid any confusion. Also, the block sequence card is required if you want to make use of the block layer card, which is the next slide. Okay, the block layer is the layering of blocks for the overset strategy. So once again, we have the same example here. Now the main block, the largest block, is the first layer. So our layer number would be 1. Now next we have embedded inside of the main block, we have the store pylon block, which is block number 2. So this is layer 2. And then embedded inside of the layer 2 block, we have the 4 thin blocks. So these would be layer number 3. So if we look at the block layer card, the block layer reuses the same grids from the block sequence, except now we're listing out the layer number. So our first block, like we said, is layer 1. Our second block is layer 2. And then the next 4 blocks are layer 3. In this example, not pictured, but we've got 3 more blocks, which we're all saying are layer 2. So you can imagine if we have 3 more store pylon blocks hanging out here that are blocks, let's see, would be like 7, 8, and 9. We could have block 7, block 8, and block 9, which are all embedded inside of the main block. So these would all be layer 2. Now it's okay that this block 7, 8, and 9 actually have a larger number than blocks 3, 4, 5, and 6, because these 2 blocks, like block 6 and block 7, don't overlap with each other. It's just, do your numbers increase relative to the blocks that they overlap with. So blocks, in this instance, 7, 8, and 9, they only are embedded inside block 1. So that's fine. An initial note on the block layering when you use this, blocks that belong to the same layer do not directly communicate with each other. So all of our layer 3 blocks, which are blocks 3 through 6, the outer boundary of blocks 3, 4, 5, and 6 will be interpolated from block number 2, and block number 2 is in layer 2. So the layer 2 block will contribute the far field boundary condition to blocks 3 through 6, who are all layer number 3. Furthermore, the layer 3 blocks, the internal portion of those blocks, will contribute their flow solution back to block 2. Meanwhile, the outer boundary condition of block 2 is obtained from block 1, and then the interior of block 2 will hole cut block 1 and contribute its flow solution back to block 1. Next, we have the mesh param card, which is parameters for the mesh generation. So we have an ID number. Next, we have ID block. This is an identification number of a block or block T card whose parameters are modified by the mesh param card. ID ELET can refer to a delete line bulk data card to delete undesired grid lines. And I've actually never had to make use of this card. But if you look at your resulting mesh and you see you've got extra grid lines in there that you don't want, you can delete them using this option. DYFact controls the spanwise mesh size near the surface of a vertical lifting surface. And then also the left and right hand sides of a body. So this is determined by dy_fact times the reference chord. And the default is 0.01 or 1%. So most cases, this gives an adequate mesh size. And then dz_fact is the vertical mesh size near the surface of a horizontal lifting surface, and then also the above and below a body. So this is dz_fact times ref c, or the default is 1% times ref c. And then next we have x growth, y growth, and z growth. X growth determines the rate at which the mesh size grows ahead and behind the Sierra 7 or the body 7. So the default here is 1.3, and then furthermore, the sign of x growth determines the outer boundary of the block. So on the left, x growth is positive, so our block is rectangular, like this. So usually for the main block, this is what you would use so that your main block is rectangular. If your block is embedded inside of another block, you may want to use the negative x growth option. So with the negative x growth, then the grid is not sheared as much. So the outer boundary follows the shape of the model. So with an embedded block, this might be useful so that you keep your embedded block as small as possible. And let's see, like I said, the default's 1.3. Y growth and Z growth are the same, but for the Y and Z directions. So in this example here, we've got this component is in this blue block here. It's the rear wing of the model, and you can see that it's embedded inside of our main block. And to minimize the amount of overlap, we want this block to be as small as possible, so we've set the X growth and Z growth options to be negative, so that the block follows the shape of the wing, so that the embedded portion of this block and the main block is as small as possible. Next we have the X, Y, and Z tolerances. X tolerance times dx min serves as a small tolerance for deleting redundant grid lines in the X direction. Now, assuming your surface panel model is set up ideally, ZEUS shouldn't need to delete redundant grid lines. If ZEUS is deleting redundant grid lines, that indicates you probably have a poor surface mesh. Add line is a flag to control the grid spacing of the chordwise Y lines ahead of the wing leading edge and behind the wing trailing edge. And then L shear L is a flag to control the Y lines emanating from the left-hand side wingtip to the left-hand side far field, should they be sheared according to the leading and trailing edge sweep angle. So for L shear equals 1, then the chordwise Y lines are sheared according to the leading and trailing edge sweep angle. If L shear L is 0, then the lines are perpendicular to the left-hand side wingtip. That is, the X coordinate is held constant. Now for a lifting surface with a swept back leading edge and swept forward trailing edge, then the chordwise spacing between the sheared chordwise Y lines could become very small as they approach the far field. So in this case, L shear L equals 0 is recommended. Another way to avoid this problem would just be to add a gap card outboard of the wing, and then that would control those chordwise Y lines. L shear R is the same except for the right-hand side wingtip. And these figures illustrate the parameters that we have. So our delta Z here, you can see we have our horizontal surface. That's our dz_fact. And then we have a vertical surface, and then our body. This is the dy_fact. And then down here, we have the add line illustration. So for the chordwise Y lines immediately ahead of the wing leading edge. The grid spacing can be controlled by add line. For add line equals 0, which is figure D here, the dx2 may not equal dxt may occur, and if add line equals 1, then dx2 equals dxt is ensured. But this add line is active only for a clean wing configuration. For F, you have a wing with a wingtip launcher. So in this case, dx2 is controlled by the chordwise divisions of the surface mesh of the launcher. Next, we have the mesh save card, which allows you to save or retrieve the mesh. So during model development, you won't want to use this card, but after you have the model developed and you're ready to start running analysis cases, you may want to use this card. So the first field is the save field. So this is a character string, either save or acquire. Save will save the flow field mesh to a file, and acquire will acquire the flow field mesh. And then file name, of course, is the file name of the data file. So if you're finding that the mesh generation module of ZEUS takes too much time, you can use this card to save the mesh once and then retrieve it for all subsequent jobs. You want to be careful using this option though, because there isn't a lot of error checking. If you go in and you change parameters of your mesh generation, ZEUS may not catch that, and it will just continue to use the old mesh that you're acquiring. And so your input deck may not match that of the actual mesh that ZEUS is using. So you do want to be careful and make sure that when you save the mesh and then you acquire it, that you're no longer changing parameters of the flow field mesh. That we've referenced the A-chord card several times. This defines the aerodynamic coordinate system. So we have an ID number. Then we have X origin, Y origin, Z origin, which define the X, Y, Z location of the origin. Delta is a pitch angle measured in degrees from the X, Z axes of the basic coordinate system to the X prime, Z prime axes of the component coordinate system, positive in this direction. So positive would be like a positive angle of attack, or nose up. This delta parameter does not physically rotate the model. Its effects are introduced in the boundary condition. Therefore, delta should be a small value. And then theta is a roll angle in degrees measured from the YZ axes of the basic coordinate system to the Y prime Z prime axes of the component coordinate system, positive in this direction. So this is, if you're behind the aircraft looking towards the nose, you can see the YZ axes. So positive theta will lift the right-hand side wing up. Theta will physically rotate the model. So the theta option can be used when you want to model a pylon underneath a wing, a pylon store in a block, and you want the pylon to be a locally horizontal surface. You can rotate the block 90 degrees using the theta option, and then you can see that after you rotate 90 degrees, the vertical pylon becomes a locally horizontal surface in that block. Next, we have the AEROZ card to define a control surface. So a control surface will be part of a AEROZ, as shown in this figure here. So the label is a unique alphanumeric string of up to 8 characters, which is used to identify the control surface. The type is the type of control surface, which can either be symmetric, antisymmetric, or asymmetric. CID refers to a chord 2R card, which defines the hinge line axis. When CID is greater than 0, then the y-axis of the coordinate system is the hinge line, and when CID is negative, then the z-axis of the coordinate system is used to define the hinge line. So in this figure, when CID is less than 0, our origin of our coordinate system is here, and then our point B is somewhere out here to define the z-axis. So that is the hinge line of the control surface. Next we have set K, which is the identification number of the panelist T1, panelist T2, and or panelist T3 bulk data cards, which list out the aerodynamic box IDs of the control surface. And remember, you can refer back to the C-AERO7 card to see how the boxes in the C-AERO7 are numbered. So in this case, this is our C-AERO7, and then we want to refer just to these boxes which define the aerodynamic boxes of the control surface. And then the set G field refers to the set 1 and or set add bulk data cards, which list the structural grid point IDs of the control surface. And then ACT ID, actuator ID, refers to the ACTU bulk data card, which defines the transfer function of the actuator attached to this control surface. We have the negative option for the CID because it's much easier to define a Z-axis of a Chord 2R card than it is to define a Y-axis of a Chord 2R card. If you're copying your model, aerodynamic model from Nastran, then you'll probably already have your hinge line defined as the Y-axis. That's fine, you can reuse it. But when setting up a model from scratch, I always use the Z-axis of a Chord 2R to define my hinge line because that's much easier. Next we have the plot arrow card, which allows you to create a file with the aerodynamic model. And I always recommend to use this card to make sure the aerodynamic model looks like what you expect. So we have an ID number, which doesn't really matter. It's just using error output. FemGrid is a flag. Character string can be either yes or no. For FemGrid equals yes, then the structural grid points are included in the plot file. When it's no, the structural grid points are not included. So I do recommend having at least one plot arrow card where FemGrid equals yes, so that you can verify that the structural grid overlap with the aerodynamic model. Offset is active if FemGrid equals yes. This will add an offset to the ID numbers of the structural grid points. I never use the offset. I always leave it as 0 because for the tech plot format it doesn't matter. The form must be tech plot. ZEUS for this particular card doesn't support any other plot styles, so that just must be tech plot. And then file name is the name of the data file on which the data is generated. The thick is a flag field, can be either yes or no, whether or not to include the thickness of the C-AERO7 due to the airfoil definitions in the PAFOIL7 card. So for thick equals yes, the plot file includes the effects of the PAFOIL7, which is the airfoil sections, and for thick equals no, then just the flat plate is generated. Now remember, in the ZEUS computational solver, the C-AERO7 essentially is a flat plate because the mesh is grown above and below that flat plate. However, the slopes of the C-AERO7 on the upper and lower surface are mapped to that flat plate, and then those slopes are used in the transpiration boundary condition. So it's good to plot both the flat plate model and the thick model to make sure that both are correct. And then finally we have mesh, and this is a flag to be either yes or no. So when mesh is yes, then the entire mesh generated by the block T, and block 1 cards are included. And when mesh is no, then only the surface panel model is included. And here are some examples. This is with thick equals yes and mesh equals no. This is thick equals no and mesh equals no. So you can see that our C-AERO7s are all just flat plates. And then we have thick equals no and mesh equals yes. We get these 3 plots. So we have the volume meshes are plotted. Next we have the plot CP card to plot the steady and unsteady pressure coefficients. So we have an ID number. Next we have sim, which can be either sim for the symmetric condition, anti for the antisymmetric condition, or asim for the asymmetric condition. ID MK refers to an MK AEROZ card. And IK has some different options here depending on what you're plotting. So for unsteady aerodynamic pressures, IK is used to specify the index of the reduced frequency in the MK AEROZ card. The frequency domain unsteady aerodynamic pressure associated with this reduced frequency will be output in the file for either the 3D contour or the 2D XY curves, depending on the mode. So when mode here is greater than 0, then we output the 3D contour plot, and when mode is less than 0, then we use the 2D XY curve format. Now for the steady aerodynamic pressures, IK is an arbitrary integer, and when IK is greater than 0, then we use the 3D contour format, and when IK is less than 0, then we use the 2D XY curve format. For the unsteady aerodynamic pressures, mode is the index of the structural mode, whose associated unsteady pressures will be exported. And then for steady aerodynamic pressures, mode is a character string that must be steady. And then form is the format of the file. So for the 3D unsteady aerodynamic pressure contour, we have TechPlot, Patran, IDEAS, FEMAP, ANSYS, Nastran, ESA, and NASTL. And the default is TechPlot. File name obviously is the name of the file. And then ID wing is only for the 2D option. So in this case, ID wing is the identification number of a C07 on which the pressure coefficients of the specified span locations are stored, and then YWPOS are those span-wise location in percentage of wingspan, measured from the root of the C07. So like I said, these two are for the 2D options. This is a resulting 3D contour plot. This looks like a steady CP plot option. Next, we have the plot surf card to plot the control surface deflections. So we have an ID number, which is arbitrary. Label is the character string that matches the label entry of an AEROZ card. Max DISP is the physical displacement in model units of the furthest distance of the control surface from the hinge line, used for visualization. Our form, we support TechPlot, Patran, IDEAS, FEMAP, ANSYS, Nastran, or NASTL. The default is TechPlot, and then we have the file name is the name of the file. The arrow name is just used for the Patran format. And these are some examples of the deflected control surface. These are actually, let's see, the label matches the AES link, not the AEROZ for these, because we have both the left and the right hand side deflected. The plot surf, I recommend using this whenever you have control surfaces to verify two things. One, that you've selected the correct aerodynamic boxes. Two, that your hinge line, you've defined it correctly and the sign of the hinge line is what you expect. Next, we have plot SLP, or plot slope. This generates a plot file for plotting the slopes of the computational surface mesh. So remember, we keep talking about the transpiration boundary condition of ZEUS, which depends on the slopes of the surface panel model. So this is where you can visualize what those slopes are that ZEUS is actually using in its computation. So we have an ID number, and then SLP WMax allows you to alter the threshold value for warning messages. So this is the threshold slope value for printing a warning message to the standard output file when the slope of a C07 element with respect to the flow direction exceeds this value, which the default is 1.5. So if the plot slope card is not in your input, then the default value of 1.5 is used. So when the slope of a box on a C07 exceeds 1.5, a warning message is printed out to the output file. And so you'll want to take a look at that and see, is this actually a problem, or is this what my model actually is? And if you have trouble In the solver of ZEUS, you can try to figure out if it's caused by this condition. Next, SLP B max is the threshold derivative of the slope with respect to x for printing the warning message on the output file when the change in slope along a body 7 with respect to the flow direction exceeds this value SLP B max, and the default here is 0.5. Next, we have the actual plot file parameters. So form must be techplot, and then file XY, we have two options. File XY is the name of the data file in which the slopes of the aerodynamic boxes are represented in an XY line style plot. And then file 3D is the name of the file in which the slopes of the aerodynamic boxes are plotted on the surface mesh as a contour plot. So as I've noted, the transpiration boundary condition of the Euler solver requires the slope on the computational surface mesh. So this is very important. Remark 3, for the calculated differences of slope on adjacent boxes on a body, the warning message is printed if they're too great. And this is because large jumps in the slope along a body 7 may prevent the solution from converging and may cause very high and low CP distributions. So in this case, you want to try to smooth out the geometry of the surface mesh, or with engine inlet boxes, make sure that the flow-through condition is specified using the P-body 7. So if we look at what the example is here, so on the left, we have the surface panel model where the fuselage and stores are modeled by body 7, and the lifting surfaces, of course, are modeled by C-Aero7. The computational surface mesh is shown on the right here. So the body 7 macro elements are modeled by square boxes with the slope distribution with respect to the x-axis represented by the color contour. And it's important to ensure the smoothness of the slope distribution because that is what is involved in the transpiration boundary condition. So if we look, just as an example here, we have a constant slope here on the nose, and then we have a 0 slope from here back. And so you can see that here, our color and the nose portion is a constant, and then it changes to green, which is just 0 for the remaining part of the fuselage. And then if we look at the wing, you can see due to the leading edge, we've got a higher slope, and then it goes back towards 0, and then slightly negative at the trailing edge of the wing. For the stores here, additionally, you can see the slope distribution along the stores. This store here, if you remember several slides back, I was talking about the sheared body box following the shape of a nearly cylindrical body 7. And this is a cylindrical body 7 type of element. But you can see that every axial station, our body box is just a square. But we've sheared the size of it to follow the size of the store. So this is a really good illustration of what exactly that is and what the computational mesh looks like to the ZEUS solver.